This is Dr. Christensen's class, and we're ready for some chemistry notes. So,
well, sort of. That's okay.
All right.
Okay. That's what you get if you make fun of me, so you're going to have to come up and do it. So, okay, chapter 3, guys. Hey, this is a new chapter. It's a cool chapter. It's one of my favorite ones. I know I say that every time, don't I? But this really is a cool chapter. We're going to expand our study beyond the nucleus. So the last chapter we studied the nucleus, so protons and neutrons, right? This chapter we're moving out farther away from the nucleus, so this would be the nucleus. Now we're going to study what's happening out here. What do you call these particles out here, guys? Electrons. Where do the electrons hang out? In the electron cloud. Okay, and so we're going to find out why electrons are significant. What do they do? Some of the things that they cause, and why they're important in chemistry, which is all really good questions. We're going to talk about and show you atomic emission spectra. Like why do we get all these colors? You guys remember how to remember all the colors that we can see in order? What's that mnemonic? You guys? Roy G. Biv, okay? Roy G. I guess it's an acronym, right? Roy G. Biv, or it's a mnemonic. So it tells you how to remember all the colors in order. What is R? Red, orange, yellow, green, blue, indigo, and violet. Okay, guys, do you know where light comes from? Okay, but
energy.
What causes light? How come the sun is producing so much light?
It has so much energy.
Yeah, it does have something to do with energy, but what particle, what part of the atom is it coming from? Electrons. Yeah, that's why we're studying electrons in this chapter. One of the reasons. Is it?
Yeah, well, I was going to say.
That's what you were going to say, Dawson?
Yes.
Good. Good job, man. Okay, so electrons cause light. We're going to talk about how they cause light. This is just another picture I picked up off the internet. A cool picture of the atom and some electrons there. And we're going to do a lab in this chapter. It's called the flame test lab, and this is a picture of what you're going to be doing. You're going to be lighting different elements on fire and watching what color they will burn. What's really cool is that all of the elements have their unique color of light that they give off. And so you will be able to see that. In fact, that's how they design fireworks, right? They put different elements in the firework, and they can make it burn green or blue or red or whatever. So some cool things about electrons. So let's get into it. If you're watching the video, we are following along in the Chapter 3 guided notes and filling in those blanks as we go through the slides. Ready? Okay. Just a quick review before we get into electrons. The development of the atomic model over time. Who did we start with? John Dalton. What did he call this model right here, John Dalton? This is the billiard ball. He just thought atoms were small, hard particles. And didn't know much else than that. Didn't know there was electrons, protons, or neutrons, or anything. Until J.J. Thomson came along. What did he call this model?
Plum pudding.
Plum pudding. The plums were what? What did he discover? The electrons. The pudding was all the positive charge was in between. Okay, so the first particle that was discovered was the electron. Do you guys remember what experiment he did to discover the electron? Yeah, the cathode ray tube experiment. That's how he was able to discover the electron. Okay, then one of his students, Ernest Rutherford, what did he discover? The nucleus. And specifically, what particle? The proton. And so now we have a nucleus in our atomic model, and the electrons are just kind of in orbit around the outside. Okay, this is called Rutherford's model. Didn't really have a fancy name for it. And then Niels Bohr, he studied what electrons were doing. What did he say electrons were doing?
Energy level.
Yeah, he called them energy levels. So this would be E1, energy level 2, energy level 3, and so forth. So he said that electrons travel around the nucleus in these circular paths called energy levels. Well, that wasn't quite true. Remember, Heisenberg and Schrodinger came along and they came up with the electron cloud model. Some people call it the quantum model, but now we just have this cloud. We don't really know what the electrons are doing, but they're out there in the cloud somewhere. Okay. Coming back to us, remember? Yeah? Okay. Oh, I forgot. What experiment did Rutherford do in order to discover the nucleus? Gold foil experiment. That's a good one to remember. Okay. Okay, things we will learn in this chapter. Things that we're going to learn in this chapter are that electrons produce light. All the light that we see, whether it's coming from the sun, the light bulb, a candle, a flashlight, it all comes from what the electrons are doing. It comes from the electrons. Okay, light travels through the air as a wave. So we're going to study waves in this chapter because we're studying light. So we're going to study the characteristics of a wave, do some calculations with waves, figure out a lot of different parts of the wave. Okay, number 3, different colors of light waves have different wavelengths, frequencies, and energies. We're going to talk a lot about these characteristics of waves. Wavelengths, frequencies, and energies. And each element emits a unique wavelength of light. Every element emits its unique wavelengths of light. Okay, we'll look at that. We'll talk about how electrons are arranged in the electron cloud. It's a little bit complicated, but we'll talk about how they are arranged. It's called electron configuration. And we'll kind of end the chapter talking about these electrons, the valence electrons. These are the most important electrons in chemistry. The valence electrons are the outermost, this outer shell of electrons. We call them valence electrons. Okay, so we've got a lot to learn. So let's start. In the early 1900s, I think you're supposed to write something down here. Scientists observed certain elements emitted visible light when heated in a flame. So in the early 1900s, a scientist was noticing that if you heated an element in a flame, it would emit visible light. It would give off light. And scientists found that each element emits a unique color of light. So every element was a little bit different color. And that the light was produced from the electrons. So, okay, every element has a different color of light, and that they were coming from the electrons. Okay, a flame test. This is the lab that we're going to do in this chapter a little bit later once we know a little bit more about light and waves and electrons. We're going to do a flame test lab. But many elements give off characteristic light which can be used to help identify them. For example, strontium. If you look on the periodic table, strontium is SR, and it's right here, number 38. It kind of burns a reddish, kind of pink color. Sodium, the normal orange color that we picture, that we have a good idea of a flame. When we see like a campfire burns orange, that's the same color as sodium. Lithium is a really cool kind of pinkish red color here. Potassium, very cool. My favorite is always the green color, and copper is what causes the green color. So copper, let me see if I can move that out of the way. So that green one is copper. All right. Light travels through the air as a wave. Light travels through the air as a wave. You're supposed to write that down. So if light travels through the air as a wave, let's talk about waves. All waves can be described by several characteristics. You don't have to write anything here. It will be on the next slide where we talk about them in more detail. But all waves have a wavelength. Guys, that's pretty self-explanatory, right? It's the length of a wave. We'll talk about that. All waves have a frequency and an energy to them. And we're going to, big part of this chapter is being able to determine a wave's wavelength, its frequency, and its energy. So we'll talk a lot about these. Okay, we're going to go through each one in detail here. a wavelength is given this symbol. It kind of looks like an upside down Y, but it's called lambda. Okay, it's another Greek letter, lambda. It is the shortest distance between equivalent points on a wave. Units are measured in meters. So we're using the metric system, so we don't measure it in feet or inches. We measure wavelength in meters. Okay, so a wavelength is the shortest distance between equivalent points on a wave. What is this symbol called again, guys? Lambda. It's called lambda. All right, let's talk about frequency. It's given this symbol, it's kind of a fancy little V. It's called mu. And it's the number of waves that pass a given point per second. So frequency is the number of waves that pass a given point per second. And the units for frequency are called hertz. And it's abbreviated as Hz. So what I would remember for this one, how to calculate frequency? Well, it's the number of waves per second. Okay, and you'll calculate it, and then your units are going to be in hertz. Hertz just means waves per second. Okay, and then finally, energy is given the symbol that actually makes sense, a capital E. And it's the amount of energy a wave has. Energy, the units for energy are joules. And joules is abbreviated with a capital J. So on the coming slides, I've got a number of practice problems. I think I've got 7 of them, where we are going to kind of go through each one and determine a wave's wavelength, its frequency, and energy. Okay. Okay, parts of a wave. Let's talk about the anatomy of a wave here. So this wave, let's talk about wavelength first. Okay, wavelength, its definition. It's the distance between equivalent points on a wave. So if we're starting up here, what is the very top of this wave called?
Crest.
It's called the crest. Okay, what's the very bottom of a wave called? A trough. And the middle, this kind of imaginary line, is called the origin. And then what's the distance between the origin and a crest? It's called amplitude. Is this also the amplitude? Could you go from origin to trough?
Yes.
Sure. And so that's called an amplitude. Now if we look at what a wavelength is, it's the distance between equivalent points on a wave. So if I start here at a crest, where's the next crest? Well, we just keep going until we're at an equivalent point. So the distance from here to there is called a wavelength. I always recommend that students go from crest to crest to find the wavelength. Because if you go from origin, say let's measure the wavelength from this point. What a lot of students will do and get themselves in trouble is just go to the next part where it crosses the origin. But would this be an equivalent point? No. See how this one, the wave is coming down into the right? Well, on this part of the wave, it's going up and to the right. That's not an equivalent point. So a wavelength from here would be where? To where it comes down again. Okay? But if you just remember it's from peak to peak or trough to trough, look, you can go here and then just kind of slide it down. Okay? And then you'll make a lot less errors with your wavelength. So peak to peak. That's what I always remember it by. Okay, practice problem number 1. It says to draw a wave and label the following parts. I want you to label the origin, a wavelength, crest, a trough, and amplitude. Okay, so practice problem number 1. So we're going to draw a wave. Okay. And now let's draw those parts. Let's draw the origin first. There's kind of this imaginary line right through the middle of it all. And guys, help me out. What do we call this part of the wave right here? That's the crest. What do we call this part of the wave down here? Trough. The origin.
Origin.
Good. And Dawson, what do we call this distance from the origin to the top of the crest?
Amplitude.
Amplitude. Very good, man. Okay, so from there to there is called amplitude. Very good. Oh, and we just got one more thing to do. What's the wavelength? Yeah, let's go from here to where? To there. That would be 1 lambda, or 1 wavelength. Okay. Now, what if I started right here? Where would the next wavelength be? Would it be right here? No. It's right here. It's equivalent points of a wave. And so that would be 1 wavelength. Okay. So here's the thing about waves. The longer the wavelength, the lower the frequency, and the lower the energy. So let's look at, I've got 3 waves over here. One's red, one's green, and one's blue. Which color, red, green, or blue, has the longest wavelength up here? Red. Yeah, you can see that the wavelength here is, a lot longer with the red. A little shorter here and even shorter here. So let me ask you this. Which wave, red, green, or blue, which one has a higher frequency? Highest frequency? Yeah, more waves per second down here, right? There's a lot more waves. When it goes up and down like this fast, that's really high frequency. There's a lot more waves per second. Which wave would have the most energy? Blue has the most energy. This one here has a lot more energy. See, notice kind of how red is kind of this lazy, kind of long wavelength. It's a very low energetic wave. And just the opposite is true. Shorter wavelength equals higher frequency. So the shorter the wavelength, we get more waves per second, so we get a higher frequency. And if we have a higher frequency, we get more energy. So, pop quiz, red. Which wave up here has the lowest energy? Which one has the least energy? The red one, right? Good job. Yeah, the red one has the least energy. There's just not, it's not very, it has the lowest frequency, so it's got the least amount of energy. Okay. So, things to remember. You have to write something here, I think. Oh, did you guys get that on that last slide? Yeah. So, longer wavelength equals lower frequency and lower energy. Shorter wavelength, though, equals higher frequency and higher energy. Yeah, a little bit tricky there. Okay, let's go through some of these. You do have to write something here. As a wave's frequency goes up, so does its energy. So which wave, guys, red or blue, has a higher frequency?
Blue.
Blue, good. It's got, yeah, there's more waves, right? There's a lot more waves per time here. So this one has a higher frequency. Which one would have higher energy? Blue has higher energy. Good. So energy and frequency are directly related. Energy and frequency are directly related. As one goes up, what happens to the other one? Goes up.
Goes up.
What if one goes down? The other one goes
down.
Down. Good job, Dawson. So yeah, that's how I remember it. Direct relationship is if one goes up, the other one goes up. And if one goes down, the other one also goes down. Okay, let's talk about wavelength and energy though. As a wave's wavelength goes up, its energy goes what? Down. Notice how the red wave here, the wavelength is very long. But if the wavelength goes up, what happens to energy?
Goes down.
Goes down. Good job. So energy and wavelength are inversely related. And there's this inverse relationship. So as wavelength goes up, what happens to energy, Dawson?
Goes down.
Goes down. Okay, what if the opposite, what if I say it the other way around? What if wavelength goes down? What happens to energy?
Goes up.
Goes up. Okay. Okay, so pop quiz real quick, guys. What kind of relationship would this be? Direct or inverse if both are going up? Direct. What if they both go down? Direct.
Direct.
What if the first one goes up and the second one goes down? That's an inverse relationship. What about the opposite of that? What if the first one goes down and the other one goes up? It's still inverse. Yeah, if they're opposite, it's inverse. Good job. Okay, practice problem number 2. It says, on the graphs below, draw a line that correctly identifies the relationship between energy and wavelength and energy and frequency. Guys, help me out with this one. As wavelength goes up, what happens to energy? Goes down. So how could I draw a line on this graph that would make sense? Start at the top left and go down? Would that make sense, guys? Would that line make sense? With low wavelength, do I have high energy? Yes. With a longer wavelength, do I have low energy? Sure. That's your answer. Good job. Good job. Okay, Delaney. How are we going to draw this line? So for frequency and energy. As frequency goes up, what happens to energy?
Goes up.
Goes up.
Goes up.
So how do we show that with a line?
Just go up with the line.
Go up with the line.
What do you say, Delaney?
Sure, what they said.
What they said? You're going to trust them?
Go up with the line, man.
Go up with the line.
Guys, think about it. As frequency goes up, energy's got to go up.
So just gonna, yeah.
Would it look like that?
Yes.
Yes, it would.
Yes,
Good job.
it will.
Good job. Dawson, this cherry Coke. Gosh, it's good. Okay. Practice problem number 3. It says draw 2 waves, one with a lower frequency and one with a higher frequency. Let's try it. I want you to draw 2 waves, one with a low frequency and one with a higher frequency. Okay. If I'm going to draw a low frequency wave, that means it doesn't go up and down all that much, right? It's kind of a lazy wave. I describe them as a lazy wave. Now, what about high frequency? You've got to have a lot of waves per second. So, I mean, it's going to go up and down really quite dramatically. Something like that. How many of you guys got that right? Good. Let's move on then. So that one's lower frequency and higher. Okay, practice problem number 4. Practice problem number 4. Delaney, you okay?
Yep.
I'm going to keep calling on you.
They're just embarrassing.
What's that?
They're just embarrassing.
They are?
Yeah. Well, kind of.
Pictures.
Oh. Okay.
That's why.
Practice problem number 4. Let's try it, guys. Which wave shown below has the shortest wavelength? The top or the bottom wave? Which one has the shortest wavelength? Shortest wavelength. So wavelength is equivalent points on a wave. So if we go from peak to peak, wouldn't this be one wavelength? Yeah. And down here from peak to peak, this would be one wavelength.
It's kind of interesting.
So which one did you guys circle? Bottom one. Okay, good job. Okay, shortest wavelength is the bottom one, so you should have circled it. Okay. Hey, this isn't too bad, is it?
No, it's
Waves? It's not that bad. Okay, practice problem number 5. Let's do it. Very easy. You guys try it. If you're watching the video, hit pause and try to answer it before you see the answer. Okay, which wave shown below has a higher frequency, the top or the bottom? Now we want higher frequency. Wait, isn't that what we did last time? Oh, shortest wavelength. Okay, higher frequency on this one. Which one did you guys circle? The bottom. Yeah, frequency is kind of like whether the wave is lazy or not. There's a lot of waves. It's got a high frequency. Okay, how many of you guys got that one right? Good. Okay, number 6. You guys try it. Which wave shown below has more energy, the top or the bottom? More energy, guys. How is energy related to frequency? As frequency goes up, what happens to energy? Goes up. So which one's more frequent? Which one has a higher frequency?
The bottom one.
Good job.
Thanks.
Hey, we got this up. Oh, how is wavelength related to energy? As wavelength goes up, what happens to energy? Goes down. So that's, how would you describe that relationship? Inverse.
Inverse.
An inverse.
That's an inverse.
Yep. Okay, I think this will be the last practice problem for this video. So, practice problem number 7. It says, if the space between the vertical lines represents 1 second, what is the frequency of the waves below? Okay, we want frequency. Guys, frequency equals waves per second. So all you have to do is count the number of waves there are and divide it by the number of seconds that you're measuring. So what would the frequency, it's given this V symbol, be for this top one? How many waves went by in 1 second? How many waves, guys? So from peak to peak, that's 1 wave, right?
Yep.
So there's 2 waves divided by how many seconds? 1 second.
1 second.
What's the frequency, guys?
2.
2 what? What's the units for frequency?
Oh, meters.
Nope.
Hertz.
Hertz. Yeah, it's that funny one. Hertz. It's 2 hertz.
2
Okay,
hertz.
try the bottom one. See if you can get the bottom one on your own. How many waves there, guys? There's 4 waves in how many seconds? 1 second. So what's our frequency? 4 hertz. 4 hertz.
4 hertz.
Okay. Okay, guys, we've learned enough to do a little bit. Before I end the video, let's review. Okay. Which wave, guys? Top or bottom? That's the top, and this one's bottom. Which one has a longer wavelength? Top. The wavelength is measured from peak to peak. Top one. Which wave, guys, has a higher frequency? Bottom. Which one has more? So this one has a higher frequency. It's going up and down. There's more waves per second. Which one has more energy? Bottom. Do we got it? Okay. We're going to stop for a second because we've learned enough to do at least the first page of the wavelength, frequency, and energy of waves worksheet. So turn your books there and see if you can complete that first page at least.